Welcome to a lesson with Dr. Powell. Let's take a look at our example in the last video where we had this graph, y is equal to t squared. And we have y and we have t. And we were looking at the point 1 right here, and we were thinking about if we narrow in our view window and we look closer and closer at the function, closer and closer up, it looks more like a straight line. The straight line that it most looks like has a slope. The straight line that it most looks like actually has a name. We call it the tangent line to the curve. And its slope is called the instantaneous rate of change, which I'll abbreviate, IROC, instantaneous rate of change. Now, the way we got to this, or we think about it, if we take average rates of change on intervals, and we make those intervals smaller and smaller and smaller, those average rates of change over time should narrow in and get closer and closer to the instantaneous rate of change. So, kind of drawing the picture, if you will, let's just think. This slope, then we get that slope, and furthermore, if we keep on going, those slopes get closer and closer to the slope of the tangent line. So we're going to be thinking about a process that takes us from average rates of change and carries us to the instantaneous rate of change. So let's get started. Okay, so suppose that here's our function. And this is 1, okay, the x value of 1. And let's suppose that we go over and make our interval. In fact, yeah, let's make our interval go this way, h, okay? So it's just h over. All right, so then we'd like to know what the slope of this is, and let's put it in terms of h. Now, why did I just label this as h arbitrarily? Because I wanted to see the behavior of what is actually happening here with the average rates of change. So if I let my run here and my slope be arbitrary, then maybe I could see what happens as this run or this h value gets really, really small. So it allows me to investigate it when I make it arbitrary, when I make it a variable. So that's going to be h. Then the question is, what is this? What's the rise? Well, I know what this is for this function. It's 1. The y value is 1. What's this y value? Oh, so what is that y value? Well, we just plug it into the function, right? Remember what the function is. And we'll label it with a f this time. F of t is equal to t squared. Okay, so, well, what are we plugging in? We're plugging in the t value, or x value, I guess, but t value in this case. So the t value right here is 1 minus h. So to get to this point, since this is a function and it depends on its input, to get the y value, you just simply plug this in. Just plug in this into f right here. And we know what that y value is. It's just 1 minus h quantity squared. So what is this distance? Wasn't it just the difference of y values, this minus that? So this is just 1 minus h quantity squared. So we could write down 1 minus h quantity squared all over h. And we can kind of picture and see that this is equal to an average rate of change over an interval from 1 minus h all the way up to 1. Okay, well, let's just algebraically work with this. All right, let's expand this and kind of get a better feel for what this will look like. So if we do that, we'll have 1 minus quantity, 1 minus 2h plus h squared all over h. Distribute the negative. So in distributing the negative, become a -1. This will change to plus. This over here will change to minus. And all right. Notice that those ones cancel out. And this is 2h minus h squared over h. You could factor an h out of the top and cancel the bottom, or just simply divide h into each term individually. Or think about this as 1 over h times this quantity. It'll distribute to each part and cancel accordingly. So whichever way you look at it, it looks like that we end up with 2 minus h when we divide this into that and into that. So this is the average rate of change. Notice as h gets small, this thing gets closer to 2. We call this, in fact, so what could we say 2 is? We can call that a limit. As h approaches 0, the average rate of change is actually equal to this. It's not equal to this when h is 0. When h is 0, look, this expression is not defined. So we can't just plug in 0 for a run. That would be impossible here for a slope, dividing by it. So we have to think about something called a limit, kind of a limiting procedure, using what it is when h isn't 0 and seeing what happens to this expression as h goes to 0. So the expression itself is not 2 minus h, because this is not 2 minus h. It's only 2 minus h when h is not 0. When h is equal to 0, this doesn't reduce. But when it's not 0, it does reduce. So really what we're doing is we're taking the limit of the average rates of change, meaning we're seeing what it gets close to, and we'll just call that limit. Basically, what that means is, what does this get close to as h goes to 0? Now, if we reduce it algebraically to something very nice like this, where we can actually plug in 0, then let's just do that. And then we'll see precisely what this gets close to. Doing so, we end up with 2. That means that 2 is the instantaneous rate of change right here at this point. That would be the speedometer reading if we knew what the odometer was. Thanks for watching.